welcome to this presentation and a short demo about building internal developer platforms leveraging Kubernetes operators. I'm George Hantzaras. I'm an engineering director at MongoDB looking after our Kubernetes operators and our enterprise customers. So our team is responsible to enable customers in two ways, either self-hosting, so using operators in order to run MongoDB databases inside their Kubernetes clusters, or managing Atlas databases through the Atlas Kubernetes operator, which is an alternative to traditional infrastructure as code. So in the presentation, we'll start with a brief introduction of internal developer platforms and what we define as platform capabilities and platform interfaces. We'll talk about the rise of Kubernetes as the first choice of underlying platform infrastructure and how its extensibility has made this possible. And at the end, we'll have a brief demo of how operators can be leveraged to build platform capabilities and platform interfaces. Now, a big part of what we'll be talking today comes is a part of an upcoming book published in a few months, hopefully around July or August. This has been a big effort roughly over the last years, and we've included a lot of guidelines on how you can leverage cloud-native tools in order to build internal developer platforms. So let's start with a quick look on IDPs, internal developer platforms, and the rise of Kubernetes as the preferred choice. So the term platform has been around for a while. In its most basic definition, it is a foundation that developers can use to build software application. It provides a set of tools and services that make it easier to develop, deploy, and manage application. We've seen that a few times. It's not something new. But the term internal developer platform has sprung up as a new term in recent years, and to kind of take things a bit further. So according to CNCF, a platform is designed in order to reduce cognitive load on developers, to provide consistent experience, and is designed to be user-friendly and improve developer productivity and developer experience. Platform engineering is the effort that goes into designing and building those IDPs. And IDPs bridge the gap between underlying what we call capability providers and platform users, such as application engineers. In doing so, such platforms implement and enforce desired practices that we call golden paths. Now, an IDP offers various integrated capabilities, usually from a variety of underlying tools and services. It can include continuous integration, continuous deployment workflows, observability tooling, managed database as a service, which is what our demo is going to be about, secret management services, and many more. Now, these tools and services and golden paths provide simplified tasks and usually are available through what we call platform interfaces. And platform interfaces can be a CLI, it can be GitOps tooling like Argo CD and Flux, or developer portals, which we've seen a lot lately, like Backstage or Port, and so on. And while there's not concrete research, there's not much data to categorically prove that the majorities of IDPs are built on top of Kubernetes, it seems to be the consensus that Kubernetes is what we call the platform of platforms. And it hasn't always been like that. A few very important developments of that is Kubernetes' extensibility improvements allow it to be to orchestrate much more than just containers or much more than just VMs. It can orchestrate many diverse workloads. Beyond the extensibility, the CNCF has fostered an amazing rich ecosystem of tools and services, and those services build upon the extensibility in order to become part of such a platform. And finally, standardization and abstraction have played a big part. So Kubernetes has become much more interoperable, and the abstractions have drastically simplified management. Now, before we go further, to understand how some of those key developments have happened, it's kind of critical to remember the fundamentals, to remember the fundamental architecture, and specifically about the control plane. So the control plane of Kubernetes is kind of the brain of the operation. It manages worker nodes, it manages application running on them. And among other components, so we have the API server, the scheduler, and so on. The one that we will dive a bit deeper is the controller manager, which is essentially a collection of controllers that together ensure that the state of the cluster matches the desired state. And we'll dive a bit deeper into that. So let's see how we can extend Kubernetes and how we can use those components to expand our platform. So digging a bit deeper into the controller manager and the control loop, those two are intertwined concepts, and it's kind of critical to understand how operators work under the hood. So the Kubernetes controller manager is a daemon, essentially, that embeds the core control loops shipped with Kubernetes. So a controller is a control loop that matches the shared state of the cluster through the API server and makes changes attempting to move the current state towards the desired state. And it's made up of several controllers. We have the replication controller that ensures a desired number of pod replicas are running for each deployment. We have the endpoints controller that maintains a list of pods that provide a particular service, and the namespace controller, and so on. Now, each controller follows what we call a control loop. We start with the get desired state. So the controller retrieves the desired state for a specific resource through the Kubernetes API server. And then we get the current state. Again, the controller queries the API server and determines the actual number of pod replicas that are currently running. And finally, the reconciliation is where the magic happens. So the controller compares the desired state and the current state, and if there's a discrepancy, it issues commands again through the API server to take corrective actions. So the control loop is the core principle behind each controller within the controller management. It's a continuous iterative process that ensures the cluster state remains aligned. So it helps us avoid configuration drift, and it continuously corrects what we want to happen in our cluster with what is happening in our cluster. So Kubernetes has a number of inbuilt controllers. They automate management of different tasks. As we said, replication pods, exposing pods externally through services, management of namespaces. And while the default controllers are kind of critical for Kubernetes to function, the custom controllers that is what provides extensibility and can help us build more functionality into our Kubernetes clusters. So custom controllers allow us to extend what types of tasks and resources Kubernetes is capable of orchestrating. They work in conjunction with CRDs, custom resource definitions, to manage custom resources specific to our use case. CRDs specify the schema for a custom resource, and this essentially creates a new API objects that a custom controller can run in Kubernetes. But how do operators and controllers fit together? So operators package up custom controllers and more to make it easier to deploy and manage custom workloads in Kubernetes. This can include various CRDs, code for multiple controllers, Helm charts, management diagnostic tools, and kind of anything that we need to make management easier. So by bundling these elements together, operators offer a self-contained unit of simplifying management of an entire application on Kubernetes. And not all Kubernetes operators are alike. So we can broadly categorize operators into two types based on the resources that they manage. We have internal operators that focus on managing resources that are running within the Kubernetes cluster. And on the other hand, we have external operators that extend Kubernetes' reach beyond the cluster, and they manage resources that reside outside of the cluster. That can be cloud resources, that can be AWS resources, for example, through an API and so on. And by leveraging the appropriate type of the two and both of those together, we can build a platform that manages both services running in Kubernetes and external dependencies in the same way. Now, enough with the theory. Let's go to the interesting stuff. So in the demo, this is a pre-recorded demo, and we'll build essentially one capability for our IDP using Kubernetes operators plus an interface to expose that to the users. Yeah, we're going to build a database as a service using MongoDB Atlas. So we'll use one operator to manage an external service through an API. And we're also going to build a GitOps interface for the platform users in order to expose that. And perfect. So, first of all, there are a few different ways to install an operator. We can do it through kubectl, Helm charts, custom automation scripts. So in our case, we'll start by installing the Atlas operator using the Atlas CLI. So the Atlas CLI is a tool we have for customers to manage their Atlas resources, and we've built an automation in there that helps install the operator in their cluster. Okay, so we have a subcommand, and we execute Kubernetes operator install, and that installs the operator components in our cluster, and also does all the necessary setup in the background, so creates an API key. We can see all the components running. And we can see the API keys that have been created by the CLI, and those have been stored as Kubernetes secret. So the next step is here is our secret. And this is what is used by the operator in order to manage this external resource. So in order to start an Atlas project, we use a simple YAML file. The kind is Atlas project. This is a custom resource. And we just apply this to our cluster. And we can see that the new custom resource has been created in our cluster. And the operator under the hood has picked that up and has used the Atlas admin API to create the project in Atlas. Deploying our first cluster, again, simple YAML file. The type is Atlas deployment. That's the custom resource we'll be creating. We'll use the project we just created, and we define anything that we want, the instance size, the region, and so on. As before, we apply this to the cluster, and we see that the Atlas deployment custom resource has been created. And again, under the hood, the operator has picked up the changes and communicated with the Atlas admin API to create the database in our cluster. Okay, so very, very simply, we created a new platform capability, which we call a DBaaS, database as a service. So we want a way to expose this now to platform users. So we'll be building a GitOps interface based on Argo CD, so users can start using that. So installing Argo again is pretty simple. There's an automation script to do that. We start by creating a simple namespace for all of the Argo operator pods to run in, and then we just use the installation script. Simple command, a few seconds, and we can see all of the Argo pods are running in the Argo namespace. So now we've also installed the Argo CD operator. Now the next step is to create an application custom resource for Argo CD. We define our application name. It's a DBaaS application, and we also define the repository we'll be watching, and the Kubernetes setup and the namespace that we want to be deploying custom resources at. So in the Argo UI, we can see that we have created the DBaaS application. And from this point onward, no engineer needs access to the cluster anymore. So we'll use the same Atlas project definition. You see the Atlas project custom resource here. The difference is, instead of using kubectl to apply this, we just do a simple git push. And we can see in the Argo UI that Argo has picked this up and has created the Atlas project resource in our cluster. And again, under the hood, the Kubernetes operator has picked up on the change and has used the admin API in order to create this new project. Going back to create our cluster through GitOps, we use the same definition file, git push. Argo CD picks up the changes in our repository, deploys the Atlas deployment, which is our cluster, and then the operator under the hood in our GitOps project has created the project. So that was the end of the demo. And since we're managing critical production infrastructure, we didn't have fireworks, and that's a good thing, as we all like to not have fireworks in the production environments. And that's it. Through this link, you can access a repository and instructions on how you can use operators, how you can kind of follow along with this demo. And yeah, hopefully you can take the next step and start using operators to build your IDP. And thank you for joining me.
Do we have any questions in the room? Try and see if this is working.
We'll see together. Test. Hey, George. Great presentation. Thank you. Bogdan, ING Hubs. Question regarding Atlas CLI. Is it only working for deploying that YAML on Kubernetes, or is it possible to do a touchctl apply on that YAML and also apply it for bare metal, for example? Is it built only for Kubernetes, or can we also do that?
Yeah, so the Atlas CLI is designed in order to manage Atlas resources, so cloud resources. The subcommand that we have built into the Atlas CLI is designed to essentially help you set up and migrate to Kubernetes. So it's only for that reason. So you can use the operator install command to help you install the operator and so on. You can use, there's another subcommand where you can download all of your configurations as YAML files and import them in your Kubernetes cluster and create the resources. But everything is around kind of migrating to Kubernetes.
Yeah, thank you.